And now in this lecture I'll answer two questions. The first question, we find out the size of angle AMQ is equals to x. We have to find out the value of angle x. And in the second question, we find out the area of this circle that is inscribed by trapezoid ABCD. So let's start with the first question. In the drawing we have a semicircle. Point O is the center of this semicircle. AB is the diameter of this semicircle. We also know that OS equals to SO. Inside this semicircle we have square PQSO. Again, our task is to find out the size of angle AMQ is equals to x. We have to find out the value of angle x. So first of all, we know that all the angles inside the square are right angles. So this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. AB is the diameter of this semicircle. So AB is the diameter. It is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to all three. All three states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point S? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. We also know that all the sides of any square are equal to each other. That is to say, side QS equals to side SO. QS equals to OS. So, you can write here that QS equals to OS. But it is given us the question that OS equals to SB. OS equals to SB. And from this equation, QS equals to OS equals to SB, we will derive that QS equals to SB. QS equals to SB. So in the next step, we will do a construction. This is to say, we will join points B and Q together by a straight line. And then we'll extend line segment BQ until it touches the semicircle. And we'll define the touching point of the extended line segment BQ with this semicircle. This point is point N. When doing this construction, we created the right triangle QSB. On the right triangle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. According to the rule that in front of equal sides in the triangle, there are equal angles. So if we define the size of this angle SY, then the size of this area must be also equal to y because they are equal to each other according to the rule that I mentioned. We also know that the sum of the angles in a triangle is equal to 180 degrees. So in triangles we have the right triangle QSB, we have y plus y, that is 2y plus 90 degrees. In total, the sum of those triangles must be equal to 180 degrees. So in the right triangle QSB, two y plus 90 degrees, in total they must be equal to 180 degrees. With again in the right triangle QSB, 2y plus 90 degrees must be equal to 180 degrees. Here we will subtract 90 degrees from the equation, and we get that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divide this equation by 2, and finally we get that the missing angle y equals to 90 degrees over 2 is 45 degrees. So this is the missing angle y, that equals to 45 degrees in its size. This is also the missing angle y, it equals to 45 degrees in size. We joined points B and Q by straight line, then we extended the straight line BQ by straight line. In this way we got line segment BN. When we extend the straight line by straight line, the result must be a straight line. So BN is also a straight line. If you focus on the left side of the straight line BN at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So each angles we have at the left side of the straight line BN at point Q, we have this angle is equal to 45 degrees in its size, plus this angle that is a right angle, plus this missing angle, the actual angle NQP. In total, the sum of those three angles must be equal to 180 degrees according to all three. Repeat again. In the left side of the straight line and B at point Q, the sum of the angles must be equal to 180 degrees according to all three. That is to say 45 degrees plus 90 degrees plus the missing angle in QP, total they must be equal to 180 degrees. 45 degrees plus 90 degrees is 135 degrees. So 135 degrees plus the missing angle NQP, in total they must be equal to 180 degrees. we subtract 135 degrees from this equation. And we get that the missing angle NQP equals to 180 degrees plus 135 degrees is 45 degrees. So the missing angle NQP equals to 45 degrees in its size. This is the missing angle NQP is equals to 45 degrees. In the next step, we join points M and N together by a straight line. And we join points N and A together by a straight line. We have peripheral angle ABN. This is peripheral angle ABN. Peripheral angle ABN, subtend or called AN. Likewise, we have another peripheral angle AMN that subtend on the same chord called AN. And because of the fact that those two peripheral angles subtend on the same chord called AN, they must be equal to each other in their sizes. According to all 16. So I pick quickly on all 16. According to all 16, peripheral angles that subtend on the same chord are equal to each other. In the drawing we have a circle. So this circle we have, this is peripheral angle AOB that subtend on chord AB. Likewise we have, this is peripheral angle ACB that subtend on the same chord called AB. And because of the fact that those two peripheral angles subtend on the same chord called AB, they must be equal to each other in their sizes. That is to say, peripheral angle AOB equals to peripheral angle ACB, or alpha equals to beta. Can I actually implement rule 16 in our drawing? Or equals in our drawing. Those two peripheral angles subtend on the same chord called AN, and therefore they must be equal to each other in their sizes. But the size of this peripheral angle ABN equals 45 degrees. Therefore, the size of this peripheral angle AMN must be also equal to 45 degrees because it is also subtend on the same chord called AN. So peripheral angle AMN equals to 45 degrees in its size. By doing those constructions, we get the peripheral angle A and B. Peripheral angle A and B subtend on AB, that is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtends on the diameter of the semicircle or a circle must be equal to 90 degrees in its size. So I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So, in the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of this circle. And according to this rule 7, peripheral angle ACB must be equal to 90 degrees in size because it subtends on the diameter of the circle. You can see that peripheral angle ACB equals to 90 degrees in its size. We can implement rule 7 in our drawing. One put in our drawing, we have triangle A and B that subtend on the diameter of the circle that is called AB. And the whole triangle A and B must be equal to 90 degrees in its size according to rule 7. So in the right triangle A and B, this is the right triangle A and B. This angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We will continue to focus on the right big triangle A and B. The right big triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. According to the rule that in front of equal angles in the triangle, there are equal sides. So in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. That is to say, side AN equals to side NB. Because of the fact that in triangle A and B, side AN equals to side NB, it means that triangle A and B is also an associated triangle. So triangle A and B is a right triangle and also an associated triangle. So currently known, the big right triangle, triangle A and B, is also an associated triangle. Because those two sides are equal to each other, and the base of the associated triangle, triangle A and B, is AB. Again, AB is the base of the associated triangle, triangle A and B. So AB is the base of the associated triangle, triangle A and B, and AB also is the diameter of the semicircle. So AB is the diameter of the semicircle. It is twice as long as the radius. So if the radius of this semicircle equals to R, then the diameter AB must be equal to 2R. So AB equals to 2R, and it is the base of this associated triangle, triangle A and B. Here we can implement rule 24. I'll repeat quickly on rule 24. According to rule 24, the perpendicular to the base of an associated triangle bisects the base. So in the drawing we have the associated triangle, triangle ABC. Triangle ABC is an associated triangle because side AB equals to side AC. BC is the base of this associated triangle, triangle ABC. And according to this rule 24, the perpendicular AO to the base BC bisect the base BC. First of all, it is a perpendicular, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 24, the perpendicular AO to the base BC bisects the base BC. That is to say, it divides the base BC into two halves. Each half equals to BC over 2. So the first half, BO, is BC over 2, the second half, OC, is also BC over 2. And of course, the first half, BO, equals to the second half, OC. So we can implement rule 24 in our drawing. Because in our drawing, we have the associated triangle, triangle A and B. And the perpendicular to the base AB bisect the base AB. That is to say, divides the base AB into two halves. Each half must be equal to AB over 2. But AB over 2 is 2R over 2, that is R. So AB over 2 is R. So the first half is the radius of the circle, and the second half is also the radius of the circle. That equals to R according to our definition. But the question is where the perpendicular N to the base AB touches the base AB. Because of the fact that the perpendicular to the base AB bisects the base AB, it means that it divides the base AB into two halves. Therefore, it must touch the base AB at its midpoint. So it is at the midpoint of the base AB. The midpoint of the base AB is the midpoint of the diameter AB, because AB is also the diameter. And we know that the midpoint of any diameter is the center of the semicircle or the center of the circle. Again, the midpoint of the diameter AB is the center of the semicircle. And the center of the semicircle is O. Therefore, in conclusion, we can say that the perpendicular from point A, from point N, will touch the base AB at point O, that is the center of the semicircle. It is a perpendicular, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And the perpendicular from point N touches the base AB at point O, that is the center of the semicircle, because it is the midpoint of the diameter AB. That is, it's the center of the semicircle, that is point O. We know that the opposite sides of a square are parallel to each other. So a square PQSO, side PQ is parallel to the opposite side OS. And we have the rule that in front of equal angles, corresponding angles in congruent triangles are equal to each other. Those two angles, 1 and 2, are defined as corresponding angles, and they are located between the parallel lines, line 1 and line 2. Line 1 is parallel to line 2. And because of the fact that those two corresponding angles are located between those two parallel lines, they must be equal to each other in their sizes. That is to say, angle 1 equals to angle 2. So we can actually implement all this one in our drawing. While putting our drawing, those two angles, they are defined as corresponding angles, and they are located between the parallel lines PQ and OS, and therefore they are equal to each other in their sizes. But the size of this angle is 90 degrees, therefore the size of this angle must be also equal to 90 degrees. Those two angles, they are both equal to 45 degrees in their sizes, therefore they are equal to each other, and they are both subtend on the base NP. This is angle NMP, that equals to 45 degrees in size and subtend on the base NP. Likewise, this is angle NQP, that is also equals to 45 degrees in size, and it's subtend on the same base NP. Therefore, you can say that those two angles are fit to be inscribed by a circle. Well, because they are both equal, they are equal to each other, and they subtend on the same base, and therefore they are fit to be blocked by a circle. So actually, this is angle PQN, that equals to 45 degrees in its size, and subtend on chord PN. Likewise, this is angle PMN, actually peripheral angle PMN, that is also equal to 45 degrees in its size, and subtend on chord PN. You can see that they are both of them inside this circle. They are peripheral angles of this circle. So that is to say they are blocked by this circle. And it is exactly according to rule 16 that says that peripheral angles that subtend on the same chord are equal to each other. Those two peripheral angles, they are both subtend on chord PN, and they are equal to each other. They are both equal to 45 degrees, and therefore they are equal to each other. So, in conclusion, you can say that we can block those two circles inside those two angles. We can block those two angles in a circle. So, in the next step, I will prove that quadrilateral NMQP, this is quadrilateral NMQP, that is a cyclic quadrilateral. That is to say, quadrilateral NMQP can be inscribed by a circle. So, what is the meaning of a quadrilateral? That it can be inscribed by a circle. This is quadrilateral ABCD. The red quadrilateral is quadrilateral ABCD. And quadrilateral ABCD is inscribed by this circle. Why quadrilateral ABCD is inscribed by this circle? Because of the fact that all the four vertices of quadrilateral ABCD lie on the circle. Point A lie on the circle, point B lie on the circle, the vertex D lie on the circle, and the vertex C also lie on the circle. For that reason, you can say that quadrilateral ABCD is inscribed by this circle, but it is blocked by a circle. So we have here those are the peripheral angles that subtend on the same chord NP. And they are both the vertex of those two peripheral angles, they are on the circle itself. The vertex M of this peripheral angle lie on the circle, and the vertex Q of this peripheral angle lie on the circle. But what happens, what is about an angle that subtends on NP, on chord NP, and it is located outside the circle, not on the circle but outside the circle. The vertex of angle NLP, this is the vertex L of the peripheral of angle NLP. It is outside the circle, and angle NLP subtends on chord NP, but it is located outside the circle. This is angle NLP that is located outside the circle, and the side of the angle NLP is 39 degrees. So we can say that all the angles that lie outside the circle and subtend on chord NP, they will be less than 45 degrees. This is angle NP, this is equals to 35 degrees in its size. You can check, for example, you can draw angle that its vertex here, and it's subtend on chord NP, the size of this angle will be less than 45 degrees. Likewise, all the angles that lie inside this circle, like this angle, that is angle NOP, its vertex is inside the circle and it's subtend on chord NP. But the size of this angle is 85 degrees. So we can say that all the angles that lie on the circle itself and subtend on chord NP will be greater than 45 degrees, while all the angles that lie outside the circle and subtend on the same chord NP, they will be less than 45 degrees. Therefore, we can say that only the angles that lie on the circle itself and subtend on chord NP will be equal to 45 degrees in their sizes. Okay, so first of all, I copied angle NQP. It is also triangle NQP to a new page. So this is triangle NQP. In triangle NQP, angle NQP equals to 45 degrees in its size. So I copied angle NQP here. This is angle NQP. This is angle NQP. That's equal to 45 degrees. And this is triangle NQP. So I copied it from the original drawing. And we know that all the triangles are cyclic. That is to say, you can block any triangle by a circle. So this is triangle NQP. As I copied from the original drawing. We can block this triangle NQP by a circle according to the rule all the triangles are cyclic. So we block this triangle NQP by this circle. So in triangle NQP we have, this is triangle NQP, but it is also peripheral angle NQP that subtend on chord NP again. This is triangle NQP, but it is also peripheral angle NQP that subtend on chord NP. I want to prove that all the angles that are located outside the circle and subtend on chord NP will be less than 45 degrees, while all the angles that are located inside the circle and subtend on chord NP will be bigger than 45 degrees. So the only angles that are equal to 45 degrees and simultaneously subtend on chord NP will be on the circle itself. Like this angle NQP, its vertex lie on the circle. So if we rotate peripheral angle NQP with the vertex Q around this circle without changing the size of angle NQP, that is 45 degrees, and without moving chord NP, it will be the axis of the angle that we move only the vertex around this circle without changing its size, and the axis is NP. This way we create infinite angles that each of them will be equal to 45 degrees in its size, and all subtend on chord NP, because chord NP is not moving. It is the axis. So out of the infinite angles that we get by moving the vertex Q along the circle, around this circle, one of the angles will be angle NMP. So angle NMP is equal to 45 degrees in size, and it's subtend on chord NP. This is angle NMP. This is angle NMP, and it is the same angle NMP is also equals to 45 degrees inside and subtend on the same chord called NP. Here, angle NMP subtend on chord NP. So in the next step, we will join points M and Q together by straight line. And in this way, if you look relative, quadrilateral NMQP. Quadrilateral NMQP is inscribed by this circle. Why? Because of the fact that all the four vertices of quadrilateral NMQP lie on the circle itself. This is angle M, that's point M that is lie on the circle, point Q lie on the circle, the vertex P lie on the circle, and the vertex N lie on this circle. So we can say that we should prove that quadrilateral NMQP is a cyclic quadrilateral because it is blocked by this circle, because of the fact that all the four vertices of quadrilateral NMQP lie on the circle itself. We can say that quadrilateral NMQP is inscribed by this circle. Therefore, we can say that quadrilateral NMQP is a cyclic quadrilateral. So if we found out that quadrilateral NMQP is a cyclic quadrilateral because it can be inscribed by a circle. So if we found out that quadrilateral NMQP is a cyclic quadrilateral. So we can block this quadrilateral by circle. So I'll block this quadrilateral NMQP by circle because it is a cyclic quadrilateral. You can see that the red circle blocks quadrilateral NMQP because of the fact that all the four vertices N, M, Q, and P lie on the red circle, and therefore quadrilateral NMQP is inscribed by this red circle. We have the rule that says that the sum of the two opposite angles in a cyclic quadrilateral is equal to 180 degrees. If you get the sum of the two opposite angles in a cyclic quadrilateral is equal to 180 degrees. So it means that in quadrilateral NMQP, the sum of those two opposite angles is equal to 180 degrees. So this is again NPQ. This is the right angle. Plus the opposite angle NMQ. In total, the sum of those two opposite angles must be equal to 180 degrees according to the rule that I presented to you. The sum of those two opposite angles is equal to 180 degrees. This is angle NPQ, that is the right angle, plus this is angle NMQ, that is equals to 45 degrees plus X. So if you found out that angle NPQ that is 90 degrees plus angle NMQ that is equals to 45 degrees plus X, in total are equal to 180 degrees. So 90 degrees plus 45 degrees is 135 degrees. 135 degrees plus the missing angle x, that is the angle that we are looking for in this question. In total, it must be equal to 180 degrees. Here we subtract 135 degrees from this equation, and finally we get that the missing angle x is equal to 180 degrees minus 135 degrees is 45 degrees. Okay, this is the missing angle x, that is also equal to angle AMQ, and it is equal to 45 degrees in its side. So angle AMQ is equal to angle x is equal to 45 degrees in its side. And that is the answer to the first question. In the next step, I'll present to you the second question, and we'll solve the second question of this lecture. In the second question, our task is to find out the area of this circle that is inscribed for trapezoid ABCD. Repeat again. Our task is to find out the area of this circle that is inscribed for trapezoid ABCD. So, first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore quadrilateral ABCD is defined as a trapezoid because it has one pair of parallel sides. The two parallel sides, that is to say DC and AB, are defined as the bases of the trapezoid. So if we define the length of the base DC as A, and the length of the base AB is B, that is to say AB equals to B units in its length according to our definition, then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases. In this case it is A plus B times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. So in conclusion, we can say that the trapezoid is a quadrilateral with one pair of parallel sides, and the area of a trapezoid equals to the sum of its two parallel bases. In this case it is A plus B times the height edge over 2. And the height edge must create 90 degrees with the two parallel bases. So in the drawing we have a circle that is inscribed by trapezoid ABCD. In addition, we know that those two angles are both right angles. This is side AB of trapezoid ABCD, that is equals to 3 units in its length. The area of this trapezoid ABCD equals to 3 square units in its size. Again, our task is to find out the area of this circle that is inscribed for trapezoid ABCD. So first of all, we'll define the relevant points to this question with letters. We'll define the center of this circle. This point is point O. We'll define the point of tendency of tangent DC with this circle. This point is point E. Likewise, we'll define the point of tendency of tangent DA with this circle. This point is point F. And finally, we'll define the point of tendency of tangent AB with this circle. This point is point G. In the next step, we'll define the radius of this circle as x. In the next step, we will join points O and G together by a straight line. Point O is the center of the circle, point G is the point of the circle itself, therefore OG is the radius of this circle, that's equals to x. So here we can implement rule 1 in our drawing. On please pick up rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius formed to its point of tendency. In the drawing, we have a circle. This is tangent AB. This is tangent AB. That is tangent to this circle is point M. Point M is the point of tendency of tangent AB with this circle. In addition, we have the radius OM, this is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius OG that is drawn to point G, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by a straight line. OF is of course the radius of this circle. That is equals to x. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and E together by a straight line. OE is of course the radius of this circle, that is equals to x, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrangle DEOF, we have 1, 2, 3 right angles. The sum of 3 right angles is equal to 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrangle DEOF we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be at least a rectangle if not a square. So we relate to this upper quadrangle DEOF as a rectangle, although that it is actually a square, but we can write to it as a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So rectangle DEOF, side FO must be equal to the opposite side DF. Side EO must be equal to the opposite side DF. But EO equals to x, therefore the opposite side DF must be also equal to x units in its length. Likewise, in the lower quadrangle FOGA, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be equal to 90 degrees in its size, and therefore quadrangle FOGA is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle FOGA, side OG must be equal to the opposite side FA. But OG is x, therefore the opposite side FA must be also equal to x units in its length. So in total, we found out that the length of side DA of trapezoid ABCD is x plus x, that is 2x. So DA equals to 2x units in its length. We define the length of side DC of trapezoid ABCD as A. It is given us the question that AB equals to 3 units in its length, and CB is the missing side, so leave it as it is. We have already proved that DA plus the opposite side CB in any trapezoid is equals to AB plus the opposite side DC. It is true according to rule 2, so I'll not repeat on the same proof again. So in trapezoid ABCD, side DA plus the opposite side CB is equal to side DC plus the opposite side AB. This is true according to rule 2. DA equals to 2x plus CB. CB is the missing side, so leave it as it is. And it is equals to DC. DC equals to A units in its length, according to our definition, plus AB. AB equals to 3 units in its length, according to what is given us the question. So in total, we found out that 2x plus CB equals to A plus 3. Here we will subtract 2x from this equation, and we get that the missing side CB is equal to A plus 3 minus 2x units in its length. This is the missing side CB. is equals to a plus 3 minus 2x units in its length. In the next step, we will do a construction. This is to say, from point C, we will draw a perpendicular on AB. Again, from point C, we will draw a perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. When doing this construction, we're going to do quadrangle DCMA. In quadrangle DCMA, we have 1, 2, 3 vertices. The sum of 3 vertices is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrangle, in the big quadrangle DCMA, we have 4 right angles, and therefore we can relate to quadrangle DCMA as right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCMA, side DC is equal to the opposite side AM. But DC equals to A, therefore the opposite side AM must be also equal to A units in its length. AM equals to A units in its length. Likewise, according to the same rule, in the same rectangle DCMA, side DA must be equal to the opposite side CM. But DA equals to 2x, therefore the opposite side CM must be also equal to 2x units in its length. What is the length of the missing line segment? Line segment MB. MB equals to AB minus AM. Again, MB equals to AB minus AM. So write it down. The missing line segment MB is equal to AB minus AM. So MB equals to AB. AB is 3 according to what is given in the question, minus AM. We just write down formula that AM equals to A. So in total MB equals to 3 minus A units in its length. MB equals to 3 minus A units in its length. In the next step, I'll copy the big right angle CMB in a new page and we will implement the Pythagoras theorem on this big right angle CMB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse CB equals to A plus 3 minus 2x units in its length. Side CM equals to 2x. And side MB equals to 3 minus 3 units in its length. Here by PT is abbreviation for Pandora stone. So actually, this is the right angle CMB, this is the curve from the original domain. In this right angle CMB, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. So I write it down. CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB equals to A plus 3 minus 2x, therefore CB squared is A plus 3 minus 2x squared. And it is equals to CM squared. CM is 2x, therefore CM squared is 2x squared. 2x squared is 4x squared. Plus MB squared. MB is 3 minus A, therefore MB squared is 3 minus A squared. So in total, we found out that A plus 3 minus 2x squared equals to 4x squared plus 3 minus A squared. We'll open the brackets on both sides of this equation according to the algebraic identity that states that A minus B squared equals to A squared plus B squared minus 2 times A times B. So according to the algebraic identity that I mentioned, A plus 3 minus 2x squared will be equal to A plus 3 squared plus 2x squared. 2x squared is 4x squared minus 2 times A plus 3 times 2x. And it is equals to 4x squared plus 3 minus A squared. 3 minus A squared, according to the algebraic identity that I mentioned, will be equal to 3 squared, that is 9, plus A squared, minus 2 times 3 times 8, that is minus 6A. We'll open the brackets of this expression and you get that A plus 3 squared equals to A squared plus 3 squared, that is 9, plus 2 times A times 3, that is 6A, plus 4x squared, minus 2 times 2x is minus 4x, so in total this expression equals to minus 4x times A plus 3. And it is equals to 4x squared plus 9 plus A squared minus 6A. We have A squared on both sides of this equation, so A squared gets cancelled. We have 9 on both sides of this equation, so 9 also gets cancelled. And finally, we have 4x squared on both sides of this equation, so 4x squared also will get cancelled. So we cancel all those expressions. We have in this side of the equation only with 6a minus 4 times x times a plus 3. While on the other side of the equation we left only with minus 6a. So in total, we found out that 6a minus 4x times a plus 3 equals to minus 6a. Here we will add 6a and also 4x times a plus 3 simultaneously to this equation. And again that 6a plus 6a is 12a. So 12a equals to 4x times a plus 3. And again, if you found out that a equals to 4x times a plus 3. Here we divide this equation by 4 and we get that 12a over 4 is 3a, so 3a equals to 4x over 4 is x, so in total this expression equals to x times a plus 3. So if we found out that 3a equals to x times a plus 3. Here we will divide this equation by a plus 3. And finally we get that x equals to 3a over a plus 3. And again, if you found out that x, that is the radius of the circle, is equal to 3a over a plus 3 units in its length. In the next step, we will calculate the area of this trapezoid ABCD according to the formula that I presented to you in the beginning of the lecture. So what is the area of trapezoid ABCD? The area of trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say DC plus AB, DC plus AB, times the height over 2. The height is cm because it's greater than 90 degrees with the two parallel bases. So times the height cm over 2. So in total, if you found out that the area of this trapezoid ABCD is equal to the sum of its two parallel bases, that is to say DC plus AB, times the height cm over 2. DC equals to a units in its length plus AB. AB equals to 3 units in its length according to what is given as the question, times the height cm. Cm equals to 2x over 2. So in total, if you found out that the area of trapezoid ABCD is equal to a plus 3 times 2x over 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. 2 cancelled 2. This expression will be equal to a plus 3 times x. So if you found out that the area of trapezoid ABCD, in total it is equal to a plus 3 times x square units in its size. But it is given as a question that the area of trapezoid ABCD is equal to 3 square units in its size. So we can substitute the area of trapezoid ABCD by 3 square units. Trapezoid ABCD equals to 3 square units according to what is given as the question, and it is equal to a plus 3 times x. So 3 equals to a plus 3 times x. But we have already found out that x equals to 3a over a plus 3, so we can substitute x in this equation by 3a over a plus 3. We'll do it now and we get that 3 equals to a plus 3 times x, and x equals to 3a over a plus 3. So in total, we found out that 3 equals to a plus 3 over a plus 3 times 3a. So we have a plus 3 in the numerator, a plus 3 in the denominator, so a plus 3 gets cancelled, and we have to only be 3 equals to 3a. 3 equals to 3a. Here we divide this equation by 3, and we get that a equals to 3 over 3, that is 1. So in total, if you found out that a equals to 1 unit in its length. So I can now, if we found out that a equals to 1 unit in its length, but we already found out that x equals to 3a over a plus 3. So now we can substitute this equation by 1, because a equals to 1. We'll do it now, we get that x equals to 3a. A is 1, so 3a is 3 times 1, that is 3, over a plus 3. A is 1, therefore a plus 3 is 1 plus 3, that is 4. So in total, we should know that the radius of the circle is equal to 3/4 units in its length. Our task is to find out the area of the circle. So what is the area of the circle? Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total, the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So if you find out that the area that we were looking for this question, that is the area of this circle, it is equal to either 9 pi over 16 square units in its size, or in terms of numbers, the area of this circle is equal to 1.767 square units in its size. And that is the answer to the second question. Repeat again, if you found out that the area of this circle that is described by trapezoid ABCD is equal to either 9 pi over 16 square units in its size, or in terms of numbers, the area of this circle equals to 1.767 square units in its size. So we finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our task is to find out the size of this angle AMQ that is equal to x. We have to find out the value of angle x. So, in the drawing, we have a semicircle. Point O is the center of this semicircle. AB is the diameter of this semicircle. In addition, we know that OS equals to SO. Inside this semicircle, we have square PQSO. Again, our task is to find out the size of this angle AMQ that is equal to x. We have to find out the value of angle x. So first of all, because of the fact that all the angles inside the square are right angles, those 4 angles are right angles in square PQSO. AB is the diameter of this semicircle. AB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point S? We have this angle that is a right angle. plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. We also know that all the sides for in square are equal to each other. So in square PQSO, side QS equals to side SO. Side QS equals to SO. But it is also given us in the question that OS equals to SB. OS equals to SB. And from this equation QS equals to OS equals to SB, we will derive that QS equals to SB. QS equals to SB. In the next step, we did the construction. That is to say, we joined points B and Q together by a straight line, and then we extended the straight line BQ by a straight line until it touches the circle. We define the touching point of the extended line BQ with this semicircle. This point is point N. When we extend the straight line by straight line, the result Bn must be also a straight line. So Bn is a straight line. So if we, well, before that, we have, by doing this construction, we created the right triangle BQS. In the right triangle BQS, in front of those two equal sides, we have those two angles that must be also equal to each other on their lengths, according to the rule that in front of equal sides in the triangle, there are equal angles. So those two angles are equal to each other. So if we define the size of this angle as y, then the size of this angle must be also equal to y because they are equal to each other. And we know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have with the right triangle QSB? We have y plus y, that is 2y, plus 90 degrees. In total, it must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle QSB, 2y plus 90 degrees must be equal to 180 degrees. Here we subtract the 90 degrees from the equation. And finally found out that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divided this equation by 2 and finally found out that the missing angle y equals to 90 degrees over 2 is 45 degrees. This is the missing angle y, that is equals to 45 degrees in size. This is also the missing angle y, that is equals to 45 degrees in size. So already mentioned before, BQ is a straight line, and when we extend the straight line by straight line, the result Bn must be also a straight line. So Bn is a straight line. If we focus on the left side of the straight line Bn at point Q, here the sum of the angles must be equal to 180 degrees according to all three. So which angles we have the left side of the straight line Bn at point Q, we have this angle equals to 45 degrees in size. This is the right angle plus the missing angle NQP, total must be equal to 180 degrees according to all three. And again, if we focus on the left side of the straight line Bn at point Q, the sum of the angles must be equal to 180 degrees. So which angles we have at the left side of the straight line Bn at point Q? We have 45 degrees plus 90 degrees plus the missing third angle and QP, total must be equal to 180 degrees according to all three. 45 degrees plus 90 degrees is 135 degrees. So 135 degrees plus the size of the missing angle and QP, total must be equal to 180 degrees according to all three. Here we subtracted 135 degrees from this equation, and finally found out that the size of the missing angle and QP is equal to 180 degrees minus 135 degrees is 45 degrees. So this is the missing angle and QP is equal to 45 degrees in its size. In the next step, we join points M and N together by straight line, and we also join points N and A together by straight line. This is wave angle NMA, wave angle NMA, subset on called AN. Likewise, This is peripheral angle ABN. Peripheral angle ABN also subtend on the same chord called AN. And because of the fact that those two peripheral angles are both subtend on the same chord called AN, they must be equal to each other on their sizes. According to rule 16, of course. So I can quickly on rule 16. According to rule 16, peripheral angles that subtend on the same chord are equal to each other. So in the drawing we have a circle. The peripheral angle AOB subtend on chord AB. Likewise, this is peripheral angle ACB that subtend on the same chord called AB. And because of the fact that those two peripheral angles are both equal, they are both subtend on the same chord called AB, they must be equal to each other and their sizes. That is to say, angle AOB equals to angle ACB, or alpha equals to beta. So peripheral angles that subtend on the same chord are equal to each other and their sizes. So we can implement rule 16 in our drawing. Because in our drawing, those two peripheral angles are both subtend on the same chord called AN, and therefore they must be equal to each other and their sizes. But the size of this peripheral angle ABN, the size of this peripheral angle ABN equals to 45 degrees. Therefore, the size of this peripheral angle AMN that subtend on the same chord called AN must be also equal to 45 degrees. So here we can implement rule 7 in our drawing. Because in our drawing we have peripheral angle A and B that subtend on AB, that is the diameter of the semicircle, and according to rule 7, any peripheral angle that subtend on the diameter of the semicircle or circle must be equal to 90 degrees in its size. Therefore, peripheral angle A and B that subtend on the diameter of the semicircle must be equal to 90 degrees in its size, according to rule 7. So in the big right triangle A and B, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the big right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. That is to say, NA equals to NB. If NA equals to NB in the right triangle NB, it means that the right triangle A and B is also an associated triangle, because NA equals to NB. And again, the right triangle A and B is an associated triangle because those two sides are equal to each other. So here we can implement rule 24. According to rule 24, first of all, AB is the base of the associated triangle AB. AB is also the diameter of the semicircle. AB is the diameter of the semicircle, so if the radius of this semicircle is R, then the diameter must be equal to 2R. That is to say, the diameter AB equals to 2R. And it is also the base of the associated triangle AB. According to rule 24, the perpendicular to the base of an associated triangle bisect the base. So the perpendicular from point N to the base AB bisect the base AB. That is to say, it divides the base AB into two halves. Each half must be equal to AB over 2. AB over 2 is 2R over 2. 2R over 2 is 2. 2R over 2 is R. 2R over 2 is R. So the first half is R, the second half is also R. But the question is where the perpendicular from point N will touch the base AB. Because of the fact that the perpendicular to the base bisect the base, it must touch the base at its midpoint. What is the midpoint of AB? AB is also the diameter, and the midpoint of any diameter is at the center of the semicircle or circle. So the midpoint of AB is at point O, that is the center of the semicircle. Therefore, the perpendicular from point N will touch the base AB at point O. So the perpendicular NO bisects the base AB into two halves. The first half is R, the second half is also R. Because of the fact that it is a perpendicular, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. So we know that the opposite sides of a square are parallel to each other. So in square PQSO, side PQ is parallel to the opposite side OS. And we have the rule that corresponding angles between parallel lines are equal to each other. Those two angles are corresponding angles, and they are located between the parallel lines PQ and OS. And therefore they must be equal to each other and their sizes. But the size of this angle is 90 degrees, and therefore the size of this angle must be also equal to 90 degrees. According to the rule that corresponding angles between parallel lines are equal to each other. So we have those two angles, that is to say angle NMP and angle NQP. They are both subtend on the same base NP. And because of the fact that those two angles that are equal to each other subtend on the same base NP, they are cyclic. That is to say they can be blocked by a circle. It's actually, according to Rule 16, it says that peripheral angles that subtend on the same chord are equal to each other. This is peripheral angle this is peripheral angle NQP. This is equals to 45 degrees inside and subtend on chord NP. Likewise, this is peripheral angle NMP. This is also equals to 45 degrees inside and is subtend on the same chord called NP. This is exactly according to Rule 16 because those two peripheral angles subtend on the same chord called NP, and therefore they must be equal to each other in their sizes. And indeed, those two peripheral angles are equal to each other because each of them is equal to 45 degrees. Okay. So, in the next step, we prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, the quadrilateral NMQP can be blocked by a circle. What is the meaning of a quadrilateral that is inscribed by a circle? This is quadrilateral ABCD that is inscribed by a circle, by this circle. Why quadrilateral ABCD is inscribed by a circle? But the circle because all the four vertices A, B, C, and D lie on the circle itself. So if all the four vertices of a quadrilateral lie on the circle, it means that the quadrilateral is inscribed by a circle, or is blocked by a circle. So in order to prove that quadrilateral NMQP is a cyclic quadrilateral, we have to prove that all the four vertices N, M, Q, and P of quadrilateral NMQP lie on the circle. Okay, so first of all, I copied a triangle PQN to a new page, and in triangle PQN, angle PQN equals to 45 degrees in its size. So usually, this is triangle PQN that according to the original domain, and angle PQN equals to 45 degrees in its size. We have the rule that all the triangles are cyclic. But again, all the triangles in the world are cyclic. Therefore, triangle PQN is a cyclic quadrilateral, that is to say, it can be inscribed by a circle. So we blocked this triangle NQP by this circle. Now, we have here this is angle PQN that is equal to 45 degrees in size, and it's subtend on chord PN. Likewise, and angle PQN, the vertex of angle PQN lie on the circle. Likewise, this is angle PMN that is equal to 45 degrees in size. It's subtend on the same chord called PN, and it is also lie on the circle. The vertex M lie on the circle itself. What happens about angles that the vertices are not lie on the circle but outside the circle? Like this angle PLN, that's obtained on chord PN, but the vertex is outside the circle. Actually, it is very easy to prove that all the angles that the vertices are outside this circle, their sizes will be less than 45 degrees. Like this angle PLN, that its vertex is L is outside this circle, this is equals to 39 degrees in its size, that is less than 45 degrees. So I can say in general that all the angles that the vertices are outside this circle and subtend on chord PN will be less than 45 degrees. Likewise, what happens about angles that subtend on chord PN and their vertices are inside this circle. This is angle PON that lie on chord P and that subtend on chord PN. Its vertex O is inside this circle. The size of angle PON, is 85 degrees. So you can say in general that all the angles that subtend on PN and their vertices are located inside the circle will be greater than 45 degrees. So only the angles that their vertices are located on the circle itself will be equal, and the subtend on chord PN, only them they will be equal to 45 degrees in its size. All the angles that their vertices are located outside the circle will be less than 45 degrees, while all the angles that their vertices are located inside the circle, the size of those angles will be greater than 45 degrees. So only the angles that their vertices are located on the circle itself and then subtend on chord PN simultaneously, they will be equal to 45 degrees in their sizes. And for that reason, we can say that if we rotate angle PQN, its vertex is on the circle, this point Q, it is located on the circle itself. If we rotate this angle around the circle without changing its size, and the axis PN will not move, only the vertex will move around the circle, we'll get all the angles that are possible that subtend on chord PN, and their vertices are on the circle. All the angles. Well, otherwise, any angle that its vertex is located outside the circle will be less than 45 degrees, and all the angles that their vertices is inside the circle will be greater than 45 degrees. So all the angles that are simultaneously subtend on chord PN and are equal to 45 degrees will be on the circle itself. So by rotating angle PQN around this circle without changing the size of the angle, that is 45 degrees, we get on the angles that subtend on chord PN and are equal to 45 degrees in their sizes. One of the angles will be angle PMN. This is angle PMN. This is angle PMN, it is equal to 45 degrees in its size and subtend on chord PN. And this is angle PMN, it is equal to 45 degrees in size and subtend on chord PN. All the other angles will be either less than 45 degrees or more than 45 degrees. So by rotating angle PQN around this circle without changing in size, we'll get all the angles that are possible that are equal to 45 degrees and subtend on chord PN. There will be no more angles. So out of the infinite angles that will be created, one of the angles will be angle PMN, that equals to 45 degrees inside and subset on chord PN. So this is angle PMN that was created by rotating angle PQN around the circle without changing its size. In the next step, we will join points M and Q together by a straight line. By joining points M and Q, we get the quadrangle PQMN. Quadrangle PQMN is inscribed by this circle. Why? Because of the fact that all the four vertices N, M, Q, and P lie on the circle itself. Therefore, quadrangle PQMN is a cyclic quadrangle. So we can write down that quadrangle NMQP is a cyclic quadrangle. So we can, that is to say, we can block this quadrangle by a circle. So actually block this quadrangle by the red circle. Why quadrangle NMQP is blocked by this red circle? Because of the fact that all the four vertices of quadrangle NMQP lie on the red circle. Therefore quadrangle NMQP is inscribed by this red circle. We have the rule that states that the sum of the opposite angles of a cyclic quadrangle is equal to 180 degrees. Think quickly on the rule. The sum of the two opposite angles in a cyclic quadrangle is equal to 180 degrees. And because of the fact that quadrangle NMQP is a cyclic quadrangle, the sum of those two opposite angles must be equal to 180 degrees. This is angle NPM, and this is angle NPQ, that is right angle, and this is angle NMQ. So angle NPQ in quadrangle NMQP, angle NPQ plus the opposite angle NMQ, in total must be equal to 180 degrees. Angle NPQ is equals to 90 degrees. This is angle NQP and NPQ, that is the right angle, plus angle NMQ, angle NMQ in total equals to 45 degrees plus X. And again, angle NPQ equals to 90 degrees and angle NMQ equals to 45 degrees plus X. In total must be equal to 180 degrees according to the rule that I mentioned. 90 degrees plus 45 degrees is 135 degrees, plus the missing angle X, that is the angle that we are looking for in this question. In total must be equal to 180 degrees. Here we subtracted 135 degrees from this equation. When we found out that the missing angle X equals to 180 degrees minus 135 degrees is 45 degrees. So this is the missing angle X. It is also equals to angle AMQ, and it is equals to 45 degrees in its size. So we finish with the first question. In the next step I will later do the second question and solve the second question of this lecture. In the second question, our task is to find out the area of this circle that is described by this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrangle with one pair of parallel sides. This is quadrangle ABCD. In quadrangle ABCD, side DC is parallel to the opposite side AB, and therefore quadrangle ABCD is a trapezoid because it has one pair of parallel sides. If we define the two parallel bases, that is to say DC and AB, are defined as the bases of the trapezoid. So if we define the length of the base DC as A and the length of the base AB as B, then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say A plus B, times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. Okay, again, a quadrangle trapezoid is a quadrilateral with one pair of parallel sides, and the area of the trapezoid equals to the sum of its two parallel bases times the height over 2. The height must create 90 degrees with the two parallel bases. So, in the moment, we have trapezoid ABCD that blocks this circle, or this circle is inscribed by trapezoid ABCD. In addition, we know that those two angles are both right angles. We know that the area of this trapezoid ABCD is equal to 3 square units in its size, and this is side AB of trapezoid ABCD is equal to 3 units in its length. Again, our task is to find out the area of this circle that is inscribed by trapezoid ABCD. So first of all, we define relevant points to this question with letters. We define the center of this circle, this point is point O. Likewise, we define the point of tendency of tangent DC with this circle, this point is point E. We define the point of tendency of tangent DA with this circle, this point is point F. And we define the point of tendency of tangent AB with this circle, this point is point G. We also define the radius of this circle as X. The next step is join points O and G together by side line. Point O is the center of the circle, point G is the point of the circle itself, therefore OG is the radius of this circle that is equals to X. The radius of G that is equals to X, the radius of G is drawn to point G, that is the point of tendency of tangent B with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by side line. OF is the radius of this circle that is equals to X, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and G together by side line. OE is the radius of this circle that is equals to X. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrilateral DEOF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral DEOF, we have 4 right angles, and therefore, according to rule 5, can relate to quadrilateral DEOF as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle DEOF, side OEO equals to the opposite side DF, but EO is X, therefore the opposite side DF must be also equal to X units in its length. Likewise, in the lower quadrilateral, FOGA, we have 1, 2, 3 right angles. And therefore this fourth missing angle must be equal to 90 degrees in its size. Therefore quadrilateral FOAG has 4 right angles, therefore can relate to quadrilateral FOGA as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle FOGA, side OG must be equal to the opposite side FA. But OG is X, therefore the opposite side FA must be also equal to X units in its length. So side DA of trapezoid ABCD in total equals to X plus X, that is 2X. We define the length of side DC as A. AB equals to 3 according to what is given in the question. CB is the missing side, so leave it as it is. We already proved that DA plus CB equals to DC plus AB according to rule 2. In the previous lecture, we already proved that according to rule 2, DA plus CB equals to DC plus AB. So I'll not repeat on the same proof again. DA equals to A, DA equals to 2X, and DA equals to 2X, plus CB is the missing side, so it is, and it is equals to DC equals to A, plus AB equals to 3 units in itself, according to what is given in the question. So in total, we found out that 2x plus CB equals to A plus 3. Here we subtracted 2x from this equation, and we found out that the missing side CB equals to A plus 3 minus 2x units in its length. This is the missing side CB that equals to A plus 3 minus 2x units in its length. in the next step, we did the construction, that is to say, from point C, we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. When you find the touching point of the perpendicular from point C and AB, this point is point M. By doing this construction, we get the quadrangle DCMA. In quadrangle DCMA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the side of this 450 degrees, total the maximum equal to 360 degrees. According to the rule, that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this 450 degrees must be equal to 90 degrees in its size. So in quadrangle DCMA, we have 4 rectangles, therefore we can relate to quadrangle DCMA as a rectangle. But we know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCMA, side DC must be equal to the opposite side CM. But DC is 2x, therefore the opposite side CM must be equal to 2x units in its length. Likewise, according to the same rule, in the same rectangle DCMA, side DC must be equal to the opposite side AM. But DC equals to A, therefore the opposite side AM must also equal to A units in its length. What is the length of the missing line segment MB? MB equals to AB minus AM. So MB equals to AB, that is 3, minus AM, that is A. So in total, MB equals to 3 minus units in its length. In the next step, I copy the right angle CMB in the new question and implement the Pythagoras theorem on this right angle CMB. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right angle CMB. This is the copy from the original domain. This right angle CMB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CM squared plus NB squared. CB is A plus 3 minus 2x, therefore CB squared is A plus 3 minus 2x squared. And this equals to CM squared. CM is 2x, therefore CM squared is 2x squared. 2x squared is 4x squared plus MB squared. MB is 3 minus A, therefore MB squared is 3 minus A squared. So total, if you found out that A minus 3 minus 2x squared equals to 4x squared plus 3 minus A squared. We open the brackets on both sides of this equation. According to the rule, to the algebraic identity, that says that A minus B squared equals to A squared plus B squared minus 2 times A times B. So A plus 3 minus 2x squared will be equal to A plus 3 squared plus 2x squared, that is 4x squared, minus 2 times A plus 3 times 2x. And it equals to 4x squared plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared, minus 2 times 3 times minus 2 times 3 times A, that is minus 6A. We open the brackets of this expression, and if you found out that A plus 3 squared equals to A squared plus 3 squared, that is 9, plus 2 times A times 3, that is 6A. And we have here 4x squared, minus 2 times minus 2x is minus 4x, so in total this expression equals to minus 4x times A plus 3. And it equals to 4x squared plus 9 plus A squared minus 6A. Here we have A squared on both sides of this equation, so A squared will get cancelled. We have 9 on both sides of this equation, so 9 also will get cancelled. And we have 4x squared on both sides of this equation, so 4x squared also will get cancelled. After cancelling all those two expressions, this side of the equation we left only if 6A minus 4x times A plus 3, and on the other side of the equation we left only if minus 6A. So 6A minus 4x times A plus 3 equals to minus 6A. Here we added 6A and also 4x times A plus 3 simultaneously to this equation, and finally found out actually that (12a) equals to 4x times A plus 3. Here we divided this equation by 4, and finally found out that 12a over 4 is 3a, and 4x over 4 is x. So in total this expression equals to A plus x times A plus 3. So in total we found out that 3a equals to A times A plus 3. Here we divided this equation by A plus 3, and finally found out that x equals to 3a over A plus 3. In the next step, we calculated the area of this trapezoid ABCD according to the formula that I presented to you in the beginning of the lecture. So the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say DC plus AB times the height CEM over 2. Again, the area of trapezoid ABCD equals to the sum of its two parallel bases, that is DC plus AB times the height CM over 2. DC is A, AB is 3, and CM is 2x divided by 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. So after equation 2, we left only with a plus 3 times x. We told them we should find out that the area of tabloid ABCD equals to a plus 3 times x per unit in its size. But it is given us the question that the area of tabloid ABCD is equal to 3 square units in its size. So we can substitute the area of tabloid ABCD by 3 square units. We did it, and we found out that 3 equals to a plus 3 times x. But we already found out that x equals to 3a over a plus 3, so we can substitute x by 3a over a plus 3. We did it, and we found out that 3 equals to a plus 3 times x, and x is 3a over a plus 3. We have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 gets cancelled, and they left only here with 3a. So in total we found out that 3 equals to 3a. Here we divided the equation by 3 and we found out that a equals to 3 over 3, that is 1. So a equals to 1 unit in its length. A equals to 1 unit in its length. We already found out that x equals to 3a over a plus 3. Now we can substitute a in this equation by 1, because a equals to 1. We did it, and we found out that x equals to 3a. A is 1, so 3 times a is 3 times 1, that is 3 over a plus 3. A is 1, so a plus 3 is 3 plus 1, that 1 plus 3, that is 4. So in total we should find out that x, that is the radius of the circle, is equal to 3/4 units in its length. Our task is to find out the area of this circle that is described by trapezoid ABCD. Actually we know that the area of any circle equals to pi times the radius of the circle squared. And therefore the area of this circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total the area of our circle must be equal to pi x squared. X is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total we should find out that the area that we are looking for in this question, that is the area of this circle, equals to either 9, 5 or 16 square units in size, or there are some numbers. The area of this circle equals to 1.767 square units in its size. Okay, thank you very much.